quiz recently, right? It's on that first, I'm pretty sure there's something similar on your first quiz. You guys, you're all looking at blank. Okay. All right. So what happens is when you have multiple terms on top and you have a monomial on the bottom, the easiest approach is just to divide all the terms first, right? So when this is the same thing as each of these terms individually divided by t squared. So 2t squared over t squared is just 2, right? So you just divide everything by t squared. So you end up with the integral from 1 to 9, 2t squared over t squared is 2, t squared root t over t squared is root t, and then 1 over t squared is 2 to the negative second. So then you anti-differentiate, you get 2t plus 2/3 t to the 3 halves plus 1 over t from 1 to 9. You plug in your numbers, and you get a nice, beautiful set with some fractions. The final answer was 292 over 9. So, blah, 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 blah. Yeah, you guys got it. So, really? You couldn't simplify root 9? Like, really? Okay. All right. Okay. So, no. So, yeah. Okay.
Put the t to the negative second in front.
Yeah. You can put the t to the negative second in front, but then you got to multiply it in. Remember, there's no such thing as a product rule for integrals, and there's no such thing as a quotient rule. You can't just do the integral of each term, and multiply it together. Just like you couldn't do the derivative of each term and multiply it together, right? Okay, if you can't do it for derivatives, you can't do it for integrals. So, yeah, watch out with that one. So make sure you divide first. Good. Okay. That's right. No, that's 33 minus 5 times. Something happened. You were really close. Oh. Okay. All right. Yeah, that looks right. I think so. Okay. You guys write with mixed numerals, huh? Okay. Is 32 and 4/9 the same thing? Let's see. 33 minus 4. Yeah, that's right. Yeah, you got it with mixed numerals. All right. Mixed numerals are like a big pet peeve of mine.
Well, they look like you're multiplying.
Yes. When you put two numbers next to each other, it's supposed to imply multiplication, but with mixed numerals, it's addition, right? It's just, I don't like mixed numerals. All right. Okay. All right. So the next one, you had to do a little bit of trig simplifying. So cosine over sine squared, you kind of split it into 1 over sine times cosine over sine, and you get cosecant cotangent. And then you think to yourself, what function has a derivative of cosecant cotangent? It's negative cosecant plus c. Good, good.
It's because
Oops. You guys got the hard part and you forgot something, which you forget for all of your antiderivatives. Right? So if this was a test, it'd be minus 1, minus 1, minus 1. So be careful. 3 points is a big deal on the test, right? Okay. Oops. Okay. All right. All right. Again, minus 1, minus 1, minus 1, minus 1, minus 1. All right. So, good job. E to the x minus 1 over x dx. What's the antiderivative of e to the x? E to the x. The antiderivative of 1 over x is ln absolute value x. Isn't it funny how it looks like every single group in this class remembered the absolute value, and in first period only one group remembered the absolute value? I like that you added a plus c minus d, just in case you felt like splitting your unknown constant into multiple unknown constants. Okay. All right. And then the last one, you had to recognize what function has a derivative of 1 over root 1 minus x squared. The 3 is just a coefficient, right? 3 just gets multiplied by the answer. So you've got to know your inverse trig derivatives, which it looks like all of you do. So, good. Now, okay, in the back there, guys, be careful. I'd have to take off a point because you changed your variable, right? Yeah, so be careful. Don't change the variable. But I love that you want to use theta for trig. So the answer is 3 arcsine x plus c. Yes?
I just missed you saying it or misunderstood. But why would the second one?
Oh, because the derivative of cosecant is negative cosecant cotangent. And since there's no negative here, you got to put it here to so that you get that double negative and it becomes positive. And guys, for your trig antiderivative, remember if the answer starts with a C, it's negative. Right? If the answer starts with a C, it's negative. You have to know for your test, you have to know all the derivatives you've learned backwards, right? So be ready to do all of your derivatives backwards. Now, obviously, we're not going to ask you every single derivative you've learned backwards, but we will probably ask a little spattering like this, right? So be prepared. If you've forgotten the derivative of arcsecant, might want to refresh your memory for it. Okay? All right. Okay, today we're doing 5.4a, which is a review of antiderivatives and a beginning of understanding applications of definite integrals. We're just going to touch on beginning of applications. Today we're going to focus more on motion and how to use our calculators. I did something first period, but I don't like how it went. So I am going to do the calculator section of today completely differently. So we're going to do something together today. We're going to learn how to use our calculators together on a problem. But before we do, we have a few other little notes to take and some things to talk about. All right, are we ready? Nitty, how you doing? You could just say indefinite integrals and net change. Or you could call it indefinite integrals and applications. Okay. All right, don't write this down. Just think for a minute. So, all right. Part 2 of the FTC is talking about a definite integral, how we find a definite integral. So the integral from a to b of f of x dx is big F of b minus big F of a, where big F is the antiderivative, right? Okay, so this is what we learned yesterday. And another way of thinking of it, remember, if big F is the antiderivative of this, that means that this is the same thing as big F prime, right? It's the derivative of big F. So you can replace this little f with a big F prime if you want, because it's the same thing. It's still F is the antiderivative of this guy. Now, why is this important? Because what it tells you is if your integrand, if the argument of your integral, if that represents a rate of change, right? A derivative is a rate of change. If that represents a rate of change, then when you compute the definite integral, what you end up with is a net change in the amount of whatever you're talking about. It's like the definite integral of the rate of change is the ending amount minus the beginning amount, and therefore it's the net change in the amount of whatever f represents. And that's what we're going to get into a lot over the next 2 days, is knowing that a definite integral represents net change. Definite integral represents net change. All right. Now, here's a few little wordy examples. Don't write these down. Let's just think about it for a minute. Okay. So, for example, and the book loves to use these subscripts. So, t sub 1 and t sub 2 when I speak them out loud, I'm just going to say time 1 and time 2. Think of it as beginning time and ending time, okay? All right, so if V represents the volume of water in a reservoir, how did they come up with this? This is an AP problem. So if V represents the volume of water in a reservoir, then its derivative is the rate of change of the volume of the water in the reservoir. Could be the rate that water's like flowing into the reservoir. It could be include a rate that water's flowing in and a rate that water's flowing out, right? You could have water coming into the reservoir, and you could have like pipes coming out that are going to homes or whatever, and water's going out of the reservoir. And so you might have some V prime that is some net rate of change based on the rate that water comes in and the rate that water goes out. So whatever it is, V prime is the rate of change of the amount of water in the reservoir. So if we do the definite integral on V prime, what we end up with, well, the antiderivative of V prime is V. V represents the volume of water in the reservoir. So this is the volume of water in the reservoir at time 2 minus the volume of water in the reservoir at time 1. So what does it give you? It gives you the change in the amount of water that was in the reservoir from time 1 to time 2. It doesn't tell you how much is in there at this time or how much is in there at this time. It gives you the change between the two times. The value of the integral is the net change in the amount of whatever that function represents. So if this is the rate of change of water in a reservoir, then the definite integral on this rate of change would be the net change in the amount of water in the reservoir between those two times. If, suppose we have a function p that represents population. So p prime would be the rate of change of the population. Now, populations can go up, populations can go down. People are born, people die, right? So you have a birth rate, you have a death rate. College Board loves to do these problems where you have multiple rates. You have like something that makes it increase and something that makes it decrease. And there's always, like when they do a population, they'll have a birth rate and a death rate. They've done birth rates and death rates. Hey, you don't ever do it for people, but they do it for animals a lot. So anyway, like they did it with birds and they did it with penguins and they've done it with like insects. Anyway, so you have a birth rate, you have a death rate. But it doesn't have to be population and it doesn't have to be water in a reservoir. There's always, with these problems, there's something that makes the thing increase and something that makes the thing decrease. They did it once where people were getting in line for a roller coaster at pretend it's like Valley Fair, right? So you have a rate that people get in line and then you have a rate that people get on the ride, right? So what is the actual rate of change of the line and then what's the net change of the number of people standing in line from some time to some time? They like amusement parks because they did another problem with the actual amusement park where they just talked about people enter the amusement park, people leave the amusement park. How many people are in the park at this time? They do that kind of stuff. But it's always people come in, people leave. They've done it with cars enter a left turn lane for an intersection, and then cars actually turn left out of the left turn lane. They do all kinds of the same stuff. But they're all the same. They did one where they did sand on a beach, and they had trucks bringing in sand to increase the amount of sand, and then the tide's washing the sand away, right? They did one with snow shoveling. So snow is falling on a driveway, and there's some girl out there shoveling the snow away, right? And it was all about the net change in the amount of snow on the driveway while it's snowing and she's shoveling, right? So it's all the same. It's just a different context every time, but it's always the same. So you have rates of stuff going in and rates of stuff going out. So this is your net rate of change, basically, for your population. So what is the definite integral? All that being said is what does the definite integral give you? It gives you the net change in the population from time 1 to time 2. Right? So once you find this number, if it's positive, it means your population overall went up. If it's negative, it means overall your population went down. If you get a negative number, say it's -5, it just means between time 1 and time 2, the net change in the population was down by 5, it doesn't mean it was down the whole time. It could have gone up and down and whatever. All it means is that between time 1 and time 2, your net change was -5, right? So it gives you a net change between 2 times. All right, let's talk motion. And this is where we're going to focus most of our attention on today, is motion. So suppose your rate is velocity. Velocity, remember, is the rate of change of the position. So since velocity is the rate of change of your position, then the definite integral of velocity, well, that's the position at time 2 minus the position at time 1, or the net change in your position. What is a word for net change in position? Displacement. Displacement. So the definite integral of velocity gives you your displacement. It's how far you are from where you started, basically. Net change in your position. Now remember, there's a difference between distance and displacement. Displacement is how far you, like your net change in your position, how far you are from where you started. Distance is the total amount that you had to, that your feet moved, total amount that you've traveled. So distance you have to do something special with it. So distance is the definite integral of the absolute value of the velocity. Displacement is just the definite integral of the velocity. You have to know both of these. If you remember, distance traveled is the definite integral of the speed. It'll help you when we get to, because speed is the absolute value of velocity, right? When we get to, well, when you get to, because I have to teach this here, but when you get to parametric equations and you have to find distance parametrically, again, just always remember definite integral of the speed. Distance is definite integral of the speed.
For the integral symbol and the numbers, sometimes they're on the top and sometimes they're to the right of the integral that's on the top. Is that any different, or is that just...
I'm going to show you why.
Okay.
Okay. So, here, I'm going to pause recording to talk about motion before we actually get into a problem. So, this is how your book kind of explained it. I don't think I want to even show this to you. Instead... Come on, get off of eraser. Go to arrow. There. Okay, go away. Let's just scroll up. Okay, instead I'd rather explain it to you with an example. So just so you know, the College Board presents, like you get 6 free response questions. Every free response question is presented in one of 3 ways. It's either presented, algebraically with a function, like f of x equals, and you get, the square root of x plus 3, right? You get a function, right? So that's one way. The second method would be graphically. So the problem is presented with a graph. And then the third way, analytically, would be with a table, right? So functions, graphs, tables. Every problem you get, you're going to have a function, a graph, or a table as your primary setup with questions, right? So motion, which is on every single AP exam that's ever been published. There is always a motion problem. If you take the BC, often the motion problem is parametric, so you won't learn how to do them until you get to BC. But the same concepts apply even in parametric world. It's just adding a second dimension. So anyway, But so they will do it in any method. Like sometimes they'll give you a velocity function, sometimes they'll give you a velocity graph, sometimes they'll give you a velocity table. But like 92% of the time when they're doing a motion problem, they're going to start you at velocity. And the reason they like to start you at velocity is because then you have to differentiate to get your acceleration, and you have to anti-differentiate to get your position, right? So like they get to cover all worlds in one problem. Okay, so here's velocity with a graph. Whoops, I think I erased the little 2 I had in here. Okay, so let's pretend this is, and you know what, I'm going to erase this B, and I'm going to say that's B, that's C, that's D. So we're going to talk a little bit about distance and displacement based on a velocity graph. So if I wanted the displacement, which is, remember, the integral from, we're going to go A to D of my velocity. Well, remember, integral is area under the curve, right? So, yeah, okay. So integral area under the curve of my velocity graph, but remember, this is net area. It's net area. So the net area, we would have, just so you know, these numbers represent areas. So we have 20 minus 8 plus 2. So my displacement would be 14. Whatever the units are. Right? Does that make sense? So above the x-axis positive, below the x-axis negative. Okay. My distance is the integral of the absolute value of the velocity. When you take an absolute value of a function graphically, what it does is it takes everything below the x-axis and flips it up, right? So if you ever have fun with, I don't know if you guys ever had fun with graphing when you first learned absolute value, right? I love to start students with an absolute value of a quadratic, and that way when they graph it, when you do the absolute value, you end up with like this thing, right? Yeah, okay, it just takes whatever's below and flips it up. All right, so the integral, definite integral of the absolute value of the velocity means that this 8 is now up here. So when you do your total distance, you get 20 plus 8 plus 2, or 30, whatever the units, feet, miles, whatever. All right, so that's distance and displacement from a velocity graph. I want to talk about the velocity graph a tiny bit more. Velocity determines direction. When velocity is positive, you're moving forward, up, right, depending on how the problem is presented, right? But forward, up, or right. When velocity is negative, you are moving backward, down, or left. So for this problem, let's just say this is horizontal motion. Then for this problem, let's say it's horizontal, and let's say it's measured in feet for like feet per second for velocity, but we're just going to call it for distance. So if our horizontal position is measured in feet, from this graph, we know from whatever our starting point was, we moved 20 feet to the right, then we moved 8 feet to the left, and then we moved 2 feet to the right. Because when velocity is positive, you're going to the right. When velocity is negative, you're going to the left. The area under the velocity, that's the net change in your position. It's how far you traveled for that section of time, right? So from whatever our starting position was, we went 20 feet to the right, 8 feet to the left, 2 feet to the right. So if they ask you, what was your position at time C? Well, they have to give you a position, right? You have no idea. Whatever it is, it's 12 units to the right of wherever you started. So what's your position at time C? Well, if they tell you, say your position, very common problem. Suppose x of A equals, I don't know, 10, right? Then what's x of C? Well, x of C would be whatever you started at plus whatever your displacement was from A to C. What's your net change in your position? It's your beginning value plus the net change. Beginning value plus net change. So what would our x of c be? It'd be 10 plus the integral from a to c, which is 12. So my position at time c would be 22 feet to whatever, based on some set coordinate plane. Anyway, just a little intro on PVA using a graph. We're about to do a great big PVA problem. So the PVA problem that we did in first period, we did by hand. We're going to do it on our calculators. So I had them walk through a calculator worksheet, which wasn't bad, but instead we're going to learn calculator use in the context of a PVA problem. All right, so go ahead and get out your calculators. There is more than one way to approach what we're going to do, but in order to make it easier for all of us to work through this together, we are all going to approach this the same way first. Then later on, I'll show you other methods, okay? So if you're thinking, I know how to find a derivative easier on this spot, that's great, wonderful. I'm so glad you already know that. We're just going to do this together using the same methods so that we can kind of stay together. Like we're going to be a family. And then afterwards, we can learn other methods. All right. So we're going to do this problem. We're going to do it on the graphing window of our calculator. So the first thing that we're going to do is we are going to put this velocity function into our y1. Whenever you have a function and you have a calculator, put that function in your y1. So clear out anything else that's in your y1 right now and put that function in. You might be using x's and not t's, that's fine. Whether you have an 83, an 84, an 89, an inspired, you could do the same thing on any type of calculator. Is anyone in here on a Casio? Oh, okay. Thank God. All right. So, yeah, I do not know how to use those Casios. Is there anyone in here who needs a calculator? Okay. All right, good. Easy. All right. So, does everyone have V of t in their y1? Okay, except it'd be x's. The first question says find the displacement from 1 to 4. So what I do when I'm doing these problems is the first thing I do is I take a glance through and I just look at all my t values. All of my t values are between 1 and 4. So the first thing I would do is go to my window and set my x value to just go from 1 to 4. Y values can be whatever you want. They can, negative 10 to 10 is standard. Y values can be whatever you want. But your x values should, I like the x values to only be 1 to 4 so that if there are other solutions that are outside of what you're supposed to be looking at, you're not distracted by them. All right, everyone have their window set? All right, go ahead and graph it if you haven't already. Call me if you have any questions. All right, everyone have a graph? Good. The first thing we're going to find is the displacement. When you are finding displacement, remember for displacement is the integral from 1 to 4 of the velocity. All right, how do you do an integral on the graph window? So on the 83, 84, you're going to go to second trace. That's your calc menu. On the 89, you're going to hit F5. Is that your calc menu? Yeah, F5. Okay. All right, so is everyone, you got it? All right, so option 7 on either calculator, option 7, you should see a little integral symbol, right? Okay, hit option 7. It's going to ask you for a lower limit. The lower limit would be 1. So you type the number 1 and hit enter. Then it's going to ask you for an upper limit. The upper limit would be 4. You type the number 4 and hit enter.
I like it.
All right.
So pretty.
It is.
The Museum of Modern Art.
Okay, so I'm going to, what is it, 4.5? So negative 4.5? Okay. So your displacement, did you all get negative 4.5? All right. All right. Everyone okay? Yes? All right. Part B. So now we're going to find distance. So distance is the integral of the absolute value of the velocity. Here's what I want you to do. I want you to go back to your y equals screen. Don't touch y1. Leave it. Okay? Go to y2. All right. In y2, we're going to type in the absolute value of y1. So absolute, the ABS function, your absolute value function, is under your math menu. So hit arrow over here. Yeah. Hit math. And then you have to go to number. And then the very first choice is ABS. If you're on 89, did you find it already?
Yeah,
oh,
it's in the catalog.
Okay, all right. It's also, just so you know, your math menu is also second 5.
Okay, yeah.
And that takes you to the same choices as the 84.
Okay.
All right. So you hit ABS, and then to type in Y1, on the 84s, you hit vars, and then arrow over to Y vars, and then hit enter, enter. So enter on function, and enter on Y1. And it'll put Y1 in there for you. If you're on an 89, how many of you are on an 89? 1 in the whole class? Wow, we had like 6 in first period. So, okay, so just you. So, here, wait. I'm going to write it for you. If you ever have to do, like for you, say you want to refer to Y1, so what you would do in your absolute value symbol is you would literally type the letter Y and the number 1, but then you have to tell it like of X. It's kind of weird. It kind of is thinking of Y1 as like kind of like an F, like F of something. So if you ever do want to refer to another like function you typed in, you type it in like Y1 of X. The other thing you could do is you can copy and paste, right? So you can always just arrow up, copy, and then paste it down.
Okay.
So either way, whatever is faster for you. Okay, does everyone now? You can graph both, that's fine. Or you can turn off the graph of one just by, you just go up. If you're sitting next to the graph, you know how it's that solid color to the left of your equation? You can hit enter on that and that'll turn it off from graphing and then you don't have to worry about it. If you graph both of them, that's fine too. I'll have to show you how to do the integral. All right, but if you just graph the second, then everything should now be positive. And go ahead and do the integral from 1 to 4. If you graphed both, did anyone graph both? Okay, if you graphed both, you do you go ahead and go to your second trace and you pick integral. And then in the upper left-hand corner, it'll tell you which graph you're sitting on, right? And you hit the up and down arrow. How do you correct one? Yeah, so you're sitting on the right one now, and then you just hit type number 1. And then
Wait, what do like a brick. Wait, how do you? What?
Good. All right. So you can either arrow over to your screen on that and turn it off, right? Or if you keep it on and You have both graphs. There's the first graph, and then there's your second graph. So let's go ahead and go to second trace. And then go down to integral. You just look at the second trace. Okay, so now, see how your cursor is telling you you're sitting on y1? And now you're sitting on y2. And now you can do the integral. You just type 1, enter, 10.167. Did everyone get around 10.167?
Yeah.
Okay.
Yeah.
All right. Good. All right. Acceleration. So go ahead. We're done with absolute values. So you can just delete y2 if you want, or if you want to keep it there and turn it off. But clear, like what we need now is we need to just get back to y1. So, oops. So go ahead and clear off y2 and regraph y1. Everyone back on a regular y1?
Yes, sir.
Okay. So to find acceleration, acceleration is the derivative of velocity, right? So you go back to your calc menu. Option 6 should say dy dx. Okay, everyone see dy dx? So hit enter on that, and then you have to tell it what number you want the derivative at. We want the derivative at 1, so just type the number 1 and hit enter. This is for the acceleration now.
Would this be the actual velocity?
Right, right. You want, yeah, turn off, you don't need the absolute value. The only time you ever use absolute value is for distance. So it's second trace,
I have 1 as well.
and then option 6. So A of 1 on, which is your V prime of 1. Did you guys get 1?
Yeah.
Let's see. The derivative velocity is 2t minus 1, so it's 2 minus 1, which is 1. It's right. It's 1. It just happens to be 1. Okay.
Oh, it is.
Oh, it says. Does everyone see the dy dx? Because it'll show you both the y and the dy dx, so make sure you look at the dy dx.
Oh, we don't.
That's okay. You have an older one. That's fine. All right. Good. Okay. So next question. Speed. Is the particle's speed increasing or decreasing at t equals 1? All right. You just found a of 1. So speed. How do I know if speed is increasing or decreasing?
Same sign. Acceleration.
When velocity and acceleration have the same sign, speed is increasing. When they have opposite signs, speed is decreasing. Look at your graph at time 1. Is your velocity positive or negative? Negative. It's below the x-axis, right? So, and we already found the acceleration is positive, right? You just found it. So since v of 1 is negative, a of 1 is positive, we would say speed is increasing at t equals 1 because a of 1 and v of 1 have opposite signs. Oh, decreasing. Sorry. Thank you. I was all like excited. Decreasing. Decreasing. Because they have opposite signs. Opposite signs decreasing. Okay, another quick question. Is the particle moving to the left or the right at time 1? Left? How do you know? Because velocity is negative. Particle is moving to the left at time 1 because v of 1 is negative or less than 0. Again, you just look at the graph and you can see it. If I needed the actual velocity at time 1, how would I find it? On your calculator? Just hit trace and type the number 1 and hit enter. And that'll give you the value at 1. You know what the nice thing is about trace? Is when you are in trace mode, it stays in trace mode. So if I need a bunch of values, so like if I hit trace, say I need the velocity at time 1, 2, 3, and 4, I could just hit 1, enter 2, enter 3, enter 4, and it'll just give me all those velocities. It kind of stays in trace mode until you get out of trace mode. All right, the last one. If the particle's position at time 1 is 20, what is the position at time 4? Take a, you don't use your, you've already got all the information written down that you need for this. Take a minute, discuss with your group. If the particle's position at time 1 is 20, what is the position at time 4? I have to mention something because first period did this problem by hand, and there were a couple things they learned that you didn't that I want to mention real quick. So displacement, I know you can all do an the integral, by hand if you had to, right? I didn't simplify. We were running short on time. So anyway, however, what if you need to do the integral of an absolute value function, right? Oops, I didn't write that right. It's down here somewhere. I don't have it anywhere. Anyway, okay, so distance is the integral of the absolute value of velocity. How do you do an integral of an absolute value function? You can't. You have to convert it to piecewise, right? And then you integrate piecewise. How do you convert this to piecewise? It's a quadratic, right? What do? Really, what you're doing is you find the zeros, right? Set the velocity equal to 0, find the zeros, make a sign line, and we're only going 1 to 4. So from 1 to 3, I know my velocity is negative. From 3 to 4, my velocity is positive. So if I want all positives for my velocity integrals, I do the integral from 1 to 3. I'm going to get a negative number. I turn that into a positive and then add the integral from 3 to 4, and that gives me the whole thing. So the only way to do distance by hand is to find all the spots where the velocity changes sign and do all those integrals separately and add them, make them all positive and add them all together. It's the only way to do it. Yeah, Cassie?
We're going to have to do this by hand. Or is it just okay?
Who knows, right? Your calculator or your test is half calculator, half no calculator. So who knows? Actually, I think your test is more like 2/3 no calculator, 1/3 calculator, but I'm not positive. So anyway, everything else here was pretty much the same. For those of you watching the video here, I'm going to very slowly scroll. Acceleration, derivative of velocity, just do it, plug it in right. Velocity, speed is decreasing because acceleration and velocity have opposite signs. Particle is moving to the left at t equals 1 because the velocity is negative. And then remember that your position at 4 is the position at 1 plus the integral from 1 to 4 of the velocity. It's the position, starting position plus the net change in the position. All right. Now, we have a getting to know you. But before we do that, there's one thing on your calculator we have not yet learned how to do. So, what time did we get out of here today? It's a Tuesday, second period. Okay, we have 5 minutes. So, one more thing. So, on your calculator, you're expected on the AP exam, when you have a calculator in your hand, you're expected to use your calculator if you need to graph a function, solve an equation, calculate a numerical derivative, or calculate a definite integral. Because of that, you have to make sure, like, the College Board, if you're calculating a definite integral on your calculator, you have to give the setup and the answer. You don't have to give any work in between. You used your calculator, right? They're expecting you to do it on your calculator. If you don't put the setup, you don't get credit for the answer. You got to put the setup. If you're evaluating an integral, you got to write the integral you're evaluating. Yes.
The AP test, is there like a calculator section?
Yes. There's 4 parts. So there's multiple choice, no calculator, multiple choice calculator, free response calculator, free response, no calculator.
Is it like 3 or 6?
No, it's 30 multiple choice, no calculator, 15 multiple choice calculator, 2/3, no calc, right? 2 free response calculator, 4 free response, no calculator. Again, 2/3, no calc. So your whole AP exam is 2/3 no calculator, 1/3 calculator. Okay. And in the 1/3 calculator part, not every question is like calculator active. So it's really even less than a third calculator because a lot of the questions on the calculator section you don't use a calculator for. Anyway, so that being said, if you use a calculator to solve an equation, you have to write the equation and then write the solution. You don't have to show how you solved it. You had a calculator. You're expected to solve it on your calculator. That's the thing we didn't touch on today. We have like 3 minutes. I think we can do this. Let's solve an equation on our calculator. So there are a couple ways to solve. I have to be honest, I truly, truly dislike the solver on the 8384. Like, I don't ever use it. If you're using it and you're getting stuck, don't even come up and ask me because I'm just going to say I don't use the solver. I'll show you how I do it. But I don't use the solver. I hate the solver. I love the solver on the 89. The 89 has like the best solver in the world. The 84 solver has a really hard time when there's more than one answer. And so what'll happen is it'll spit out one answer and we're like, but I know it's quadratic. I know there's 2 answers. What's the other answer? And then you have to do all this shuffling and changing of your range that you're looking at in order to force it to spit out the other answer. So I don't use the solver. So if I'm on an 83 or an 84, the way I solve an equation is I just go to my graph window. So just for the heck of it, do you guys still have that function in Y1? So what's the function? X squared
minus X
is X minus 6. All right, let's find where this equals -2. I don't know. What do we got? Does it equal -2 anywhere in that window?
Yeah.
Somewhere? Okay. All right, so let's find out where this equals -2. So suppose I want to know where this thing equals -2. The way that I do it personally is, so some people like to put the left side in Y1, the right side in Y2, and find point of intersection. I am not a fan of that either, because your point of intersection could be somewhere way off the window. I personally like to set it equal to 0. Whoops, +2, so -4. I like to set it equal to 0 and find the zeros. So if you go to Y1 and just type in x squared minus x minus 4 equals 0, or just x squared minus x minus 4, sorry, in Y1, not equals 0, just x squared minus x minus 4 and graph it. The solution to that equation would be that spot where it crosses the x-axis. So if you go to your calc menu and you choose 0, it's option 2, then you move the little cursor a little bit to the left of the 0 and move it a little bit to the right and then hit enter. And sometimes it asks you for a guess and you just hit enter again. If it's taking a long time to move the little cursor to the left and move it to the right, like if you're sitting there hitting the arrows over and over and over, if you know the 0 falls between like 1 and 2, you can just hit the number 1, enter, and the number 2, enter, and it'll look in between them. Right? Anyway.
I'm not sure what's up with that though.
Okay. All right, guys, I'm going to